Hi and welcome back. This is part 3 of section 9.7, graphs of the 4 other trig functions. This time around my assistant is Ariana, and she and I are going to be talking to you about graphs of the cosecant and secant functions. Okay, so we're going to start with the cosecant function, and again, our goal on all of these graphs is to kind of get a little intuition into what these graphs look like, so that you can get comfortable with them and be able to draw them even if you don't have a graphing calculator in front of you. Okay, so we want to first talk about f of x equals cosecant x. Now remember, cosecant of x is the cousin to the sine function, so it's the reciprocal of the sine function. And you might remember from part 1 that there was that reciprocal identity that said that cosecant of x is the same as 1 over sine x. Okay. So before we try to draw the cosecant graph, because it's built on the sine function, I'm going to draw a picture of that sine function. And in fact, eventually this is going to be my picture of my cosecant graph. So I'm going to try and draw the sine function kind of lightly on here. I want all of the important pieces. And we'll look eventually at 2 periods. So I'll start at negative 2 pi and work my way up to positive 2 pi. All right, now I'm going to draw the sine function in blue. So you might not be able to see it as well, but that's okay. If you can kind of get a sense of it, that's all that really matters. So here is our sine function. So we have a hill, and then we have a valley, and same in the opposite direction. Okay, and the height of 1 and a height of negative 1. Okay. Now, this is our sine function here, and again, I didn't label that, but there it is. Our cosecant function is the reciprocal of sine. So we want to kind of think about what reciprocal behavior is. So if you have a number that's a really tiny number, and then you take that tiny number and you flip it upside down. In other words, if you take its reciprocal, you look at 1 over that tiny number, it turns out that that gives you a really, really big number. So that might not really make sense, but here's what I want you to try. I want you to try, on your calculator, take a really tiny number, something like 0.002. That's a good number to look at. And then what I want you to do is I want you to look at 1 divided by 0.002. Okay. And so 0.002 is definitely well, I think it's a pretty tiny number. 1 divided by 0.002, if you type that into your calculator, I did this ahead of time, I got 500. So if you have a tiny number, the reciprocal, or 1 over that tiny number, gives you something that's pretty big. 500 is a pretty big number. Okay. So when you have a tiny number, its reciprocal is big. On the other hand, if you have a big number and you take its reciprocal, 1 over big, what you get out is something tiny. So for example, if you plug in a number like 2,000, 1 divided by 2,000, well, I wrote this down ahead of time, is 0.0005, which is pretty darn tiny. Okay, so 1 over tiny gives you a big number, and 1 over big gives you a tiny number. Okay, the last type of reciprocal behavior that I want to talk about is the number 1. So check that out. We're going to go over here to do this one. If I have the number 1, and I instead take its reciprocal, so 1 over 1, I get 1. So the reciprocal of 1 is itself. The same with negative 1. If I take negative 1 and I look at its reciprocal is also itself. And it can be kind of upsetting to turn numbers upside down. That's probably why she's crying right now. Anyhow, okay. So if you're like, wow, Diane, hold on a second. I'm not sure I get this whole tiny and 1 over tiny is big and 1 over big is tiny. I encourage you to pick your favorite small number and look at what happens when you type in 1 over that small number in your calculator. See what you get out. Take a minute and pause the video and try that. Okay, the same with big numbers. Pick your favorite big number, type in 1 divided by that big number, and hopefully you'll get something that is tiny. Okay, so that being said, we are now ready to graph our cosecant function. Okay, so, oh, you know what? I guess there's one more thing I should say, and that is that the reciprocal of 0, 1 divided by 0, well, that is definitely a thing that we don't want to have. That is undefined. And again, dividing by 0 makes us cry. Okay? Okay, well, let's go back to our graph. Here we have our sine function, and our sine function is 0 at negative 2 pi, negative pi, 0, pi, and 2 pi. So when we look at the reciprocal of 0, our graph, our cosecant graph, which is our reciprocal, is going to be undefined. So we are going to have a vertical asymptote every time the sine function is 0. So every time the sine function touches the x-axis, in other words, the sine function has a y value of 0, our reciprocal graph, the cosecant function, will have a vertical asymptote. Okay? Every time that our sine function has a height of 1, our reciprocal function, our cosecant function, will also have a height of 1. So our cosecant function is going to touch our sine function at the tops of the hills, and the reciprocal of negative 1 is itself as well. Okay, so let's think about this first hill right here from the sine function. At the top of the hill, the y value is 1. But look here at this beginning of the hill. The y value right here is a pretty tiny y value. Really, I don't know how tiny that is, but it's pretty tiny. When I take its reciprocal, the reciprocal of a tiny number is going to be really big. So really tiny y value, reciprocal, is going to be up through the ceiling. Okay. So our graph is going to look something like this. It's going to come down, it's going to touch at a height of 1, and then it's going to bounce back up again. Everywhere that the sine function has a tiny y value, the cosecant graph has a really big y value. Same thing will happen over down here on the negative side. And for the bottom half, a similar idea happens, but with negative values. So we have it's kind of a U shape, pops up and comes down. So here is our graph of cosecant of x. Now, the sine function in the middle is not technically part of the graph, so I might, after I've used it as my guidance, I might erase it, and so that all I have left is my cosecant function. So here it is, our cosecant function. All right, now, if you wanted to graph this on your calculator, you wouldn't be able to just type in cosecant of x, but what you can graph is 1 divided by sine x, and it should give you that picture right there. All right, so properties of this function, properties of our cosecant function look like this. We have our domain, and our domain is every possible x value except for where the vertical asymptotes are. So all x values except x equals 0, plus or minus pi, plus or minus 2 pi, etc. Our range, this one's a little bit weird, so pay attention to this part. Take a look at our range. Between -1 and +1, there are no y values. Okay? So what that means for us is that our range starts with y values that are starting at -infinity, and then they go up to -1, and then they stop. So -infinity up to -1. And I want to include -1 because, yep, our y value at -1 does occur, so I have a square bracket. And then I skip until I hit a y value of +1. And then I get every single positive y value after 1, so from 1 to +infinity. And I want to include both of those intervals, so I put a union sign in between. So that's our domain and our range. Our period. Well, to get one period of the cosecant function, I need one upward-facing u and one downward-facing u to create the full period. So a period will go from 0 to 2 pi. So the length of one period is 2 pi. And our final observation is that we do have some vertical asymptotes. And the vertical asymptotes are all of the places where the domain does not allow. So our vertical asymptotes are x equals 0, x equals plus or minus pi, x equals plus or minus 2 pi, etc. All right, so that is our cosecant function. You want to get comfortable knowing what this picture looks like. You want to be able to draw this picture, be able to construct it, and be able to talk about its properties. All right, so we have now talked about 5 out of 6 of the trig graphs. Our final graph is our secant graph, and I encourage you to kind of think about how that secant graph will work. So when I think about the secant graph, secant is the reciprocal of cosine. So I'm going to play the same game as I just did with cosecant. So secant of x is the same as 1 over cosine of x. So I'm going to start by drawing the cosine graph just like I did with sine before. So I need some important features. Boom, 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 boom. So we have pi over 2, pi, 3 pi over 2, and 2 pi. And in the negative direction, the same thing. But now, instead of talking about the sine function, we want to look at the cosine function. So I'm going to sketch the cosine function. Here it is. Here's one period of the cosine function. Here's a second period of the cosine function. We have a height of 1 and a lower value of -1. And we want to think about reciprocals. So everywhere that our cosine function is 0, our reciprocal function, the secant function, will be undefined and will have a vertical asymptote. So we have vertical asymptotes at negative 3 pi over 2, negative pi over 2, positive pi over 2, and positive 3 pi over 2. Okay. Places where cosine has a height of 1, the reciprocal, the secant of x, will also have a height of 1. Places where cosine has a height of negative 1, the reciprocal, secant, will also have a height of negative 1. Okay? Tiny y values on cosine mean big y values on secant. So our graph will look like that U shape, but slightly shifted from the cosecant graph. So we have two downward facing U's. One upward facing U in the middle, and then here we get half of an upward facing U. And we have half of an upward facing U over here on the left. And so what we have graphed now is the graph of y equals secant x. The way I kind of think about this is when I have sort of a hill on the cosine function or a hill on the sine function for the other graph, when we look at the reciprocal, what's happening is this thing is blowing up in the opposite direction. So every hill and every valley on this cosine function corresponds to sort of an explosive U on the secant function. Okay, so I'm going to erase the cosine function here in the middle because that was just part of our guidance. And now we are ready to write down some properties of f of x equals secant x. Our domain, the allowable input values are everything except for the vertical asymptotes. So all x values except x equals plus or minus pi over 2, plus or minus 3 pi over 2, etc. Our range, well, we have all of these negative y values from negative infinity up to negative 1. And then we have nothing in the middle. And then we have y values from 1 to positive infinity. Our period is 2 pi. I can definitely see that because I have one downward and two half upward facing U's. And the vertical asymptotes are x equals plus or minus pi over 2, plus or minus 3 pi over 2, etc. By the way, I made a typo up here and you should fix that. All right. So we have just gone on a speed date with the cosecant of x function and the secant of x function. All right. Thanks for listening.